Yes, you guessed it. We are talking about force today. I just want to say thank you to Mr. George Lucas and Mr. John Williams for that beautiful music. I want to make sure that we appreciate that. Yes, we are talking about force today. That was the Star Wars theme song, in case you were confused, because they use the force, and so are we. So we're going to talk about force today and realize it's really all around us. All right, there's several things that force can do. Force can make objects move. Okay, make sure this is going to be stuff you're going to start writing down. So force can make objects move. Force can also change how things move. Okay, for example, if something's already moving, it could make it move faster or make it move slower. That's changing how it moves. Force can also change the direction of motion. Okay, so anytime you have a change in direction, there must be some kind of force doing that. Okay, so a force is really any push or pull. All right, some of you are familiar with that because maybe you have siblings that you've pushed and or pulled. My sons often do that, so they're applying force. All right. And now, we can also use force to make things happen. This unit, hopefully you've noticed this, is called dynamics. This is a study of why objects move. Why do they move? Now, we've already studied moving objects, and we'll study that more in the future. But this unit is for studying why they move. Okay, once again, we go back to the concept of a push or pull is now called a contact force. Okay, once again, back to you're pushing your sibling, there must be actually some kind of physical contact to make that happen. Now, field forces are a little different. If it helps you, most of you may have heard of a force field before. All right, if that helps you figure it out, you don't have to actually be touching that. All right, so a really good example that you're probably used to is gravity, because gravity is not physically in contact with you, yet it's holding you to the earth right now. So a good example of field force is gravity. Okay, there's four types of forces. Four types of forces. Sorry, my PowerPoint had a problem there for some reason. So, strong nuclear forces, weak nuclear forces, electromagnetic forces, and gravitational forces. Really all we need to know is these two guys right here are the strongest. Okay? These are actually keep protons and neutrons together. That's a strong nuclear force. Whoops. Protons and neutrons together. That is the strongest force, strong nuclear force. Weak nuclear force has to do with beta decay, which I know you're interested in, but we're not going to get to today. And then after that, we have electromagnetic forces. This has to do with protons and electrons. Okay, helps them. That's why electrons don't escape. And then gravitational force, what we just talked about, is the weakest force, okay, such as the Earth holding us down, right? Earth holding, I don't have to write that down, you know that. Earth holding us down. So once again, the strongest, 1, 2, 3, 4. So strong nuclear is the strongest. Weak nuclear is not quite as strong as that, but still very strong. The electromagnetic force is a little bit weaker than that, and the weakest force that we're going to talk about is the gravitational force. Okay, all these are different types of field forces, by the way. Force. By the way, do we know who this is? If not, you should feel slightly embarrassed right now. If you need to, you can pause the video and Google it. I'm fixing to tell you, but I just want you to feel thoroughly embarrassed by not knowing who this character is. This is Yoda. Okay? It's not in your notes, but it's something that you should probably know. All right, here you go. Force is a vector. Okay, we already know this, but I'm going to write it down again. That means it has magnitude and direction. Oh, yeah. Feel free not to write the oh, yeah down, but still, vector has magnitude and direction. The symbol that is F, once again, with the arrow above it, because it is a vector. The direction matters. The SI unit is newtons, and we'll always just use the letter N, and we'll talk more about that as we go along. So now, Newton has 3 laws of motion. Okay, I'm going to go quickly through this, so if you need to pause it to write it down, because you really are going to be responsible for all of this. I just wanted to, that's why I gave you a couple lines on your sheet of paper. Okay, it's the law of inertia. You've probably heard inertia before. It's an object at rest stays at rest, and an object with a constant velocity continues with a constant velocity unless unbalanced forces act on it. We understand the rest part usually by this time, but we have a little bit of an issue with the constant velocity part. Okay, if it's already moving, it's not going to start moving faster or slower unless some unbalanced force acts upon it. Okay, so just want to remind you of that. So, because that's something we struggle with sometimes. A really good example of that is a car won't turn on an icy road. If you try to turn, it's icy, the car will continue to go. Another good example of that is if you're in your car, if you slam on the brakes, your body continues to want to move forward. That's another example of inertia. Okay, try to get this box out of the way. Sorry if it's in the way. All right, Newton's 3 laws of motion. Now we're on the second law of motion, law of acceleration. The acceleration of an object is directly proportional to the unbalanced force acting on it, and it's inversely proportional to the mass of the object. That's a lot of different fancy words I have colored there for you. All of that can be summed up in the equation right here. I still want you to write this down. Okay, that's why I gave you the lines to do it. But I want to make sure you understand that F equals ma. Okay, that's kind of important. I'm even going to star it a couple times, I think, because even when I was in college, the best guess in physics is F equals ma. Okay, F sub net, we'll talk about net force in just a second, and then an acceleration point in the same direction, then the net force is the resultant or the unbalanced force. We'll talk more about that as we go along. The third law of motion is the law of action and reaction. So once again, at any point you need to pause it to write this stuff down, as I'm going kind of quickly through it, that's fine. For every action, there's an equal and opposite reaction. Okay, we understand that, hopefully, but sometimes we get a little confused. Action-reaction forces are always in pairs, okay? Now, to be an action-reaction pair, those typically have to be in contact, or there could be a field force between them. They act on 2 different objects. Okay, there's a couple of examples of that. I actually have an example on the next page. An example of a third law, action-reaction pair, is a hammer hitting a nail. It's a pretty common example because most of us are at least familiar with that. We may not be as skilled at it, but we understand that a hammer hits a nail and that makes the nail go in. They're actually equal and opposite. The force pairs there, you have the hammer and the nail, or you actually have the nail and the piece of wood also. There's 2 different force pairs in that example. Force is a vector. It's drawn as an arrow. Let me get that out of your way. All right, we already talked about that before. Just reminding you of that. The arrow length tells you the magnitude, and of course the arrow itself gives you the direction. In different ways you could write it down. 115 newtons at 45 degrees south. We probably won't use pounds very often. We'll probably stick with stuff like this. 45 degrees south or northeast. Sorry, it's kind of early. All right. The force is a vector. Have I said that yet? I think I've said that 3 or 4 times. Possibly important. Feel free to pause the video and say, oh yeah, if you would like. All right. So once again, same magnitude, different direction means a different force. So right here, these could be 2 different examples. Okay, it's referring to these right here. Even though they have the same magnitude, if they're different directions, then they're different forces. So we have balanced and unbalanced forces. Balanced are equal in size. They cancel each other out. There's no movement or change in movement. Once again, or change in movement. So that could be a constant velocity. Once again, pause if you need to, because I'm going through quickly on some of this. Unbalanced forces are not equal in size. They do not cancel each other out. An object will change speed or direction. Okay? Once again, speed or direction, because either one of those is changing in a vector because direction matters. Net force. Net force is adding all the forces together. We'll do free body diagrams in a minute, and you'll do a lot more in class, and that'll be visual examples of how we will add all of the forces. There's lots of forces in lots of different directions. Balanced forces, you have net force of 0 newtons, a net force of 0 newtons if it's balanced. Unbalanced means there's some, we say non-zero, that just means there's some number. Okay, it could be 1, 2, it could be 24, I don't know, okay? We will talk about this more when we get free body diagrams. All right? Yay! I know you're excited about talking about that more, so we will. So I know you're anxious for it. Balanced and unbalanced. Imagine you're playing tug of war. You and your friend pull with the same force. Would you move? What if you pull harder than your friend? All right? So neither of you move if it's balanced. Okay, once again, if it's balanced, then you will not move. But if you pull harder, that's not a really good example, but if you pull harder, that means you apply more force, then it'd be unbalanced. Of course, now we'll talk more about how that equals force is mass times acceleration. So if one has much more mass, that could also affect that. We'll talk more about that. Free body diagram example of book sitting on a table. If you have a book sitting on a table, a free body diagram is actually going to be, you're just going to use a dot to represent the object. So that's the object, which in this case is the book, okay? The book is the object. Now it has a force that's going up and a force that's going down, okay? The force going up is F sub n. That n stands for normal. Okay? Normal force is like a table acting up against gravity. The force of gravity, okay, F sub g, the force of gravity is weight. Okay, so the object's weight is holding it down, and the normal force of the tables is holding the object up. If you don't have the normal force, it would just fall through the table. We'll do more examples. And just remember, may the m times a be with you.